Welcome. Let's take a look at using the substitution technique to evaluate definite integrals. In this case, we have the integral from 0 to 2 of x times e to the x squared over 4 dx. So one way of interpreting this integral, since the integrand is positive, is as the area under the function, represented by the integrand, between that function and the x-axis. So here's a visual representation of what this integral evaluates. Now, as we start thinking about evaluating this, one of the first things I find helpful is to factor out any constants. And this particular function I could imagine as being multiplied by 1/4. So what I mean is that I'm going to think of this as 1/4 times the integral from x equals 0 to x equals 2 of x times e to the x squared dx. And when I'm using the substitution property, often what I'm looking for is one of two things: a composition of functions that's kind of obvious, or a product where one factor of the product is a derivative of the other factor. So as I look at this particular integrand, I notice that I have a composition of functions where my exponent in the exponential function is x squared, and that gives me a clue to what I might want to do with regards to substitution. That is, I might want to let u equal x squared and see how this plays out. What kind of new integral, transformed integral, might this produce? So if u is equal to x squared, then du is equal to u prime of x dx, or in this case, u prime is 2x dx. So let's pause there first. I'm changing my integral from a function depending on the variable x to depending on the variable u. So first of all, let's investigate our differential. Notice that in our differential we need 2x dx. I've got the x and I've got dx. I'm missing this factor of 2. So let's go ahead and multiply by 2 and by 1/2. And 2 times 1/2 is 1, so we haven't changed the value here of this integral. The next thing we need to be cognizant of is that in this transformation of the integral from depending on the variable x, we need to also attend to implications for our limits of integration. These original limits of integration are representative of the variable x. We want to go ahead and find new limits of integration that are representative of the new variable u. So what we'll do is our upper limit of integration is x equals 2. So we need to transform that to a new value for u, and u is simply x squared, so u will be u squared. U will be 2 squared, which is 4. My lower limit of integration is x equals 0. So transforming that as well, my new limit of integration u will be u squared, which is 0, or is 0 squared. Notice that we're depending on this defined relationship between x and u. So what does my new integral look like? Well, in front of the integrand, I've got 1/2 times 1/4, so that's 1/8. I'm integrating from my lower limit was 0. My new lower limit is 0. So the transformation kept the lower limit at 0. My upper limit was 2. Originally, my new upper limit is 4. So I have the integral from 0 to 4. And then looking at our integrand, we have e to the u. So e to the u. And note that this 2 times x times dx is my new differential du. So this 2, this x, and this dx, they all combine to become du. So we've gone from an integral where the integrand was essentially more complicated to an integrand that's rather simple. It's e to the u and something that's easily evaluated. And if we think about this in a similar context, that is the area between the function and the x-axis on the interval from 0 to 4, we can compare and we can see that what we're really claiming here is that the area here in yellow on the left is equal to the area here in blue on the right. And the advantage here on the left is that this integral is much easier to evaluate. So let's go ahead and evaluate this integral. So we will have 1/8. Now the antiderivative of e to the u is e to the u. And we're evaluating that from u equals 0 to u equals 4. Evaluating at 4 first, we'll have 1/8 e to the 4th minus 1/8 e to the 0 power. Now recall that e to the 0 power is 1. So we have 1/8 e to the 4th power minus 1/8 times 1, or just 1/8. And so there's the value of this definite integral. And this value represents the area shaded here in yellow, and also the area shaded here in blue. I hope you find this helpful.